Assalamualaikum. Today we are going to present about the ice Cherenkov radiation. Ice Cherenkov refers to detecting Cherenkov radiation in ice, especially in neutrino detectors like the Ice Cube Neutrino Observatory at the South Pole. Cherenkov radiation is a blue light that produced when a charged particle, like an electron or muon, travels faster than light does in that medium. It's like a sonic boom, but instead of sound, it's light. This method is used in neutrino detectors, especially at the Ice Cube Neutrino Observatory located at the South Pole. It's placed 1.5 to 2.5 kilometers deep in the Antarctic ice. The main goal is to detect high-energy neutrinos from the space. So first, their main purpose is to detect neutrinos, which are tiny, nearly massless particles that pass through almost everything. Next, ice Cherenkov detectors help us to understand the universe. Neutrinos travel across space without being absorbed or deflected, so they can carry pure information from the most extreme parts of the cosmos, like a direct message from the stars. They also help us in studying the particle physics. By observing neutrinos, we can learn about their mass, how they change type, and if they break certain laws of physics. These detectors can even monitor the Earth. Since some neutrinos are created by radioactive decay inside the planet, studying them helps us understand the Earth's core and internal heat. And finally, they can detect supernova early. A sudden burst of neutrinos is often the first sign of a star exploding, giving astronomers a head start to observe it.
The Ice Cube Neutrino Observatory is located between 1.5 and 2.5 kilometers beneath the Antarctic surface, where it's pitch dark and free from background light, ideal for detecting extremely faint signals. Within this deep, transparent ice, which is the clearest naturally occurring solid on Earth, over 5,000 light sensors called digital optical modules, or DOMs, are strategically spaced out. In this medium, light can travel more than 100 meters before attenuating significantly. But if it's completely dark down there, where is the light coming from? Well, it comes from the high-energy neutrinos. When one of these neutrinos interacts with the atomic nuclei in the ice, it produces a secondary charged particle, usually a muon. If this particle moves faster than light does in ice, it emits Cherenkov radiation, which can be seen as a bluish light. This is possible because light slows down when traveling through a medium like ice, due to interactions with the atom in the material. However, a high-energy particle, like a muon, doesn't interact in the same way. It can pass through mostly unimpeded and continue traveling near the speed of light in a vacuum. So, while the speed of light in ice is reduced, the muon can still move faster than that local limit, causing it to emit Cherenkov light. The DOMs detect this Cherenkov light. By recording when and where the light hits each sensor, researchers can reconstruct the path and energy of the original particle. This allows them to infer the direction and properties of the neutrino that caused it. Through this method, the Ice Cube Neutrino Observatory essentially turns a cubic kilometer of Antarctic ice into a telescope for neutrinos.
In 2013, Ice Cube made a groundbreaking discovery by detecting the first ever extraterrestrial neutrinos, nicknamed Bert and Ernie. These particles had energy over 1 peta-electron volt, proving that high-energy neutrinos come from outside our solar system. Then, in 2018, Ice Cube traced a high-energy neutrino back to a blazar, marking the first time a cosmic neutrino was linked to a specific source. This helped confirm that blazars can be powerful cosmic accelerators. Since then, Ice Cube has continued contributing to a supernova detection, dark matter searches, and cosmic ray studies. Looking ahead, the Ice Cube Gen 2 upgrade is underway. It will expand the detector's volume by 10 times, improve sensor sensitivity, and add radio antennas to detect even higher energy neutrinos. This next phase will help us uncover more about the extreme universe and the fundamental nature of particles. We find Ice Cube fascinating because it shows how we can detect neutrinos, tiny invisible particles from space. Using the ice beneath the South Pole, we discovered the first cosmic neutrinos and even traced one back to a blazar, helping us learn where these particles come from. Through IceCube, we're exploring supernova, dark matter, and cosmic rays, and with its coming upgrade, we'll discover even more about our universe.